Picture the scene. You're sitting right there in the exam hall. The clock is relentlessly ticking down, the tension in the room is thick enough to cut with a knife, and you turn the page of your Cambridge Mathematics past paper. Specifically, let's say it's a famously challenging question from syllabus code 0580 or maybe 0606 Additional Mathematics. Now, I want you to consider two very different students tackling this exact scenario. First up, we have Alex. Now, Alex is a hard worker, no doubt about it, but under pressure, Alex overloads every single answer with raw mathematical facts, just writing furiously, throwing everything at the page, but providing absolutely no structural analysis. And then we have Sam. Sam's approach is different. Sam rushes through the paper, frantically crunching numbers in the calculator, but completely and entirely misses the specific requirements of the command words in the prompt. Look, let's be honest, both of these are extremely common approaches, and unfortunately, both are fundamentally flawed. They will cost you marks. So welcome to this explainer. Today, we are going completely under the hood to transform your approach to Cambridge Additional Mathematics. We are building an architectural blueprint for answering exam questions. By the end of this, you are going to know exactly how to design your answer like a master architect. We're talking about ensuring that every single mathematical paragraph, every calculation, and every sketch is an absolute structural masterpiece.
The harsh reality of the exam room is crystal clear when we look at Alex and Sam's flawed answers. Take a standard trigonometric graph question. Alex tried to explain it by just dumping every single fact about sine waves they'd ever memorized. Sam just plotted a few random points and quickly moved on to the next page. Today, we are pulling directly from senior examiner insights to show you exactly how to secure what we call method marks and avoid the critical traps that literally cost thousands of students their grades every year. The primary complaint, coming straight from the actual marking rooms, is that most students lose incredibly easy marks on trigonometric graph examples. We're talking about questions comparing a simple y equals sine x to a transformed y equals 3 sine 2x. Students constantly stumble over whether the period should be calculated in degrees or radians. The examiners see thousands of papers, and they see these exact same tragic mistakes over and over again. But listen to me carefully. After we go through this, you won't be one of them. We are going to systematically break down what examiners actually want to see from you.
Here is our highly structured agenda for deconstructing those examiner expectations today. Number 1. The Exam Mastery Blueprint. Number 2. Core Mathematical Principles. Number 3. The Technical Procedural Framework. Number 4. The Method Mark Strategy. And finally, number 5, top examiner warnings.
Okay, let's really dive into this by starting with a massive, crucial question. It's a question that senior examiners continuously ask when reviewing past papers from syllabus codes 0606, 4024, 4037, and even 4040. Why on earth do students find interpreting complex mathematical texts and data so hard? I mean, think about it. Alex and Sam actually know their basic formulas, right? They've studied. So why did they both crash and burn on that trig question? Well, the answer lies in the psychological pressure of the exam itself, combined with a fundamental misunderstanding of what is actually being tested. It isn't just about what you have rote memorized, not at this level. It is entirely about how you decode the problem in front of you. The core difficulty isn't usually the arithmetic itself. The true challenge is the interpretation of complex, layered constraints that are intentionally hidden right there within the wording of the question.
Section 1. The Exam Mastery Blueprint, or as I like to call it, shifting cognitive domains.
To permanently fix this interpretation issue, we have to understand the theoretical architecture of the exam itself. Now, think about the distinct psychological domains you're operating in. Cambridge examiners don't just want to know if you can punch numbers into a calculator. That's way too basic. If you approach a high-level analysis question with low-level memorization tactics, you are inevitably going to hit a ceiling on your grade. It's a guarantee. You have knowledge and understanding down at the base, you've got application sitting in the middle, and you have analysis up at the very top. To conquer that top-tier analysis domain, you must decode specific command words, words like show that, evaluate, or sketch. This is exactly where the Peel framework comes into play. That's point, evidence, explanation, and lick. And yes, before you ask, it absolutely applies to mathematics too. When you're justifying a mathematical step, you make your point, you provide evidence through your rigorous calculation, you explain the geometric or algebraic meaning, and you explicitly link it back to the core demand of the prompt. But hey, before we continue, subscribe to our YouTube channel Ace the Exams at acedexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, jumping back in. Notice how a truly correct mathematical answer always explicitly links the calculated numbers back to the visual reality of the graph?
So, the crucial point we're driving at here is that this framework builds into true, unshakable exam mastery. The official syllabus explicitly states that top-performing students exhibit connected, conceptual understanding that is completely transferable to unfamiliar contexts. That word transferable is everything. This means you aren't just learning how to blindly solve one specific equation you've seen before, you are learning the underlying architecture of mathematical logic. When you face a completely novel, weird-looking question on your 0606 paper, you don't panic. You rely on these cross-topic connections. You realize, this question about kinematics might actually require my knowledge of quadratic curves, or, wow, this coordinate geometry problem seamlessly blends with simultaneous equations. Referencing and utilizing these cross-topic connections is exactly how you secure those significantly higher, top-tier marks.
Which brings us to Section 2, Core Mathematical Principles. Mastering y equals sine x versus y equals 3 sine 2x.
We are now entering the transformation phase of the blueprint. Let's look at a classic notorious hurdle, the basic graph of y equals sine x versus the transformed graph of y equals 3 sine 2x. Think back to our friends Alex and Sam. All their frantic errors only dissolve into those beautiful green check marks when they rewrite their answers to actually explain the why behind the numbers. For y equals 3 sine 2x, they must explicitly state that the 3 at the front represents a vertical stretch, giving the wave an amplitude of 3. This brilliantly illustrates the massive difference between merely understanding a basic principle and possessing the transferable skills to handle complex data relationships. Imagine trying to rewrite this under pressure. Think about the period of the graph. Your basic sine wave has a period of 360 degrees, or 2 pi radians, right? But the moment you introduce that 2 inside the function, the 2x, you are compressing the entire graph horizontally. The new period becomes 360 divided by 2, which is 180 degrees, or simply pi radians. And here is where students throw away marks. You absolutely must pay attention to the domain given in the question. Is the examiner asking for degrees or radians? Pinpoint the transformation, calculate the exact new parameters, and check your units before your pencil even touches the paper.
Mastering these variables relies heavily on what we call the method marks strategy. This is your ultimate psychological safety net during the exam. Method marks, which are usually denoted by a big M on the examiner's marking scheme, are awarded for the correct analytical process and procedural execution. This means you get points even if your final numerical answer is slightly off due to a silly calculator slip. These marks are the literal scaffolding of your architectural masterpiece. If you just write down a final wrong answer, with no working, you score 0, nothing. But if you lay out your logical steps clearly, showing your substitution, showing your algebraic manipulation, you capture those crucial method marks along the way.
Let's move on to Section 3, the technical procedural framework. Deconstruct, solve, evaluate. But real quick, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS, to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. Let's get right back to the framework.
All right, this is where theory becomes cold, hard practice. You cannot just jump straight into solving. That is exactly what Sam did earlier, and that is exactly why Sam lost half the marks on a question they actually knew the math for. You have to deconstruct the architecture of the prompt first. Like a master architect, you construct your answer by meticulously following a highly specific, logical progression of steps. Step 1, deconstruct the question and extract the relevant data. Step 2, select your analytical framework. Step 3, execute with crystal clear mathematical notation. And Step 4, present your final answer with the correct terminology. Let's put this to the test right now with Challenge 1, the data scan. Imagine a complex transformed trigonometric function in front of you. You have a 60-second timer counting down. Don't calculate yet. Just scan the data. What is the maximum height? What is the minimum? Where exactly does the curve cross the axis? By extracting this raw data first before you do any math, you are building an unshakable foundation to guarantee your method marks.
To ensure you execute this flawlessly under intense exam pressure, you need to use a simple memory hack to internalize the data interpretation process. DSEP. Deconstruct, select, execute, present. Or, if it helps you remember it better, think, does Sam eat pie? Honestly, whatever mnemonic gets those 4 letters permanently locked into your brain. Because when you open that exam booklet and the anxiety tries to take over your mind, you just write DSEP right at the top of the page. It instantly grounds you. It forces your brain completely out of panic mode and squarely into the structured procedural framework that examiners reward so heavily.
Section 4. The Method Mark Strategy. Thinking like an examiner.
Top-scoring candidates demonstrate elite critical analysis by continuously moving through this problem-solving execution cycle. Let's explore exactly how examiners evaluate this by entering Challenge 2, Find the Flaw. I want you to listen closely to this flawed sample paragraph from a student. The function y equals 3 sine 2x represents a wave. It has a maximum value of 3 and a minimum of -3. The graph intersects the x-axis and repeats its cycle every 360 degrees. Okay, did you spot the fatal flaw? The examiner commentary on this is totally ruthless. The student correctly identified the amplitude stretch, sure, but they completely ignored the horizontal compression. The graph repeats every 180 degrees, not 360. That one single sentence destroys the conceptual integrity of their entire answer. This brings us straight into Challenge 3, speed writing. Imagine you have exactly 30 seconds on the clock to write one perfect Peel paragraph explaining why the period of y equals 3 sine 2x is pi radians. The clock is ticking. Point: the period of the function is pi radians. Evidence: the coefficient of x is 2. Explanation: this applies a horizontal compression by a scale factor of 1/2. Link: therefore, 2 pi divided by 2 equals exactly pi radians. Boom. That is absolute mathematical perfection. When you are drawing evidence-based conclusions, you absolutely must follow strict comparative analysis rules. This is especially true when a question asks you to directly compare two functions. You can't just state random facts in isolation, you must use comparative connectives. For example, while both graphs pass through the origin, the transformed graph has an amplitude 3 times larger. You must identify both the similarities and the differences. You have to support every single claim with numerical evidence derived straight from the functions. And if it's appropriate to the syllabus, you must identify limitations. For instance, noting that a particular model only applies within the specific, restricted domain provided in the exam prompt.
Section 5. Top Examiner Warnings. Avoiding Common Pitfalls.
So, we've built the framework, we've executed the strategy perfectly, and now we are opening up the official principal examiner reports to reveal the absolute biggest hazards. Listen up, because even students who know the math inside and out will lose easy marks if they commit any of these 3 formatting and presentation errors. Mistake number 1, forgetting to include proper format. If the question specifically asks for exact values, and you write down a rounded decimal from your calculator instead of leaving it as a surd or in terms of pi, you lose the mark immediately. Mistake number 2, failing to check presentation. I'm talking about ambiguous handwriting where your 5 looks exactly like an S, or drawing a careless, straight, sketchy line through a curve on a graph sketch. Mistake number 3, providing generic, contextless answers. If the math model's a real-world scenario, your final concluding sentence must reflect that physical reality.
And this brings us to the ultimate non-negotiable golden rule. A generic answer will always fail. You must precisely link your terminology to the given scenario. If the y-axis represents velocity and the x-axis represents time, you do not just write, "the graph goes down." You must state that the object is decelerating. Every single piece of mathematical evidence you provide has to be anchored securely to the framework of the question itself. As you process this entire blueprint, I want you to seriously ask yourself, how are you going to apply these exact principles to completely transform your next practice session? Because the tools are now squarely in your hands. You are no longer Alex randomly dumping information onto the page, hoping something sticks. You are no longer Sam rushing blindly and misreading command words. You are the architect. You know how to deconstruct the prompt, you know exactly how to capture every single method mark, and you know how to build a mathematical answer that examiners absolutely love to grade. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. The blueprint is yours. Now go build it.